So earlier this week, we started talking about different formats that we have for quadratic functions. On Monday, we talked about vertex form and graph of quadratic functions. Yesterday, we brought in standard form, and we looked at how we can swap between standard form and vertex form. Today, we're going to look at standard form and vertex form again. We're going to see our graphs again, and then we're also going to talk about tables again. I know we looked at a couple of tables yesterday when we were looking at swapping between standard and vertex form and being able to check our work with those graphs. I also pulled up a table so we could pick out our y-intercepts. So we're going to see tables again today as another way to represent a quadratic function. So on page 12, we're starting with a function in vertex form. Okay, so remember, vertex form tells me the vertex of my function. That's why we call it vertex form. So my vertex would be -4. Remember, it's always opposite sign for that number I pull out of parentheses with x, and then 5. So my vertex is at the point -4, 5. Now I want to change this to standard form. I want that alternate option for my function. So to change this to standard form, where I have x plus 4 squared, that means I have x plus 4 times x plus 4, right? That's what squared means, that thing times itself, plus 5. So to change this to standard form, I'm going to distribute here and then combine my like terms. So I have x squared plus 4x plus 4x plus 16, and then still our plus 5 at the end there. And then I'm going to combine my like terms so I have standard form. So I have y equals x squared plus 8x plus 21. Now that's standard form as well. Remember, we talked about this yesterday. Standard form gives me the y-intercept. My c there at the end, my constant term, tells me the y-intercept for my graph. So my y-intercept is going to be at 21. Now, I have 2 points on my graph. I know the vertex and I know the y-intercept. But 2 points doesn't give me a really good picture of my graph. It doesn't give me a really good image. So I want some more points here. So I'm going to use a table to get some more points. Now, remember, we can always graph a function using a table. Take some values for x, plug them into your function, and see what you get for y. I'm going to be a little strategic about the values that I pick for x and how I organize my table. And I'll talk more about y here in just a minute. But I'm going to put my vertex towards the middle of my table. I'm going to put my vertex, which is -4, 5, towards the middle of my table. And then I'm going to pick x values around my vertex x value. So if I go bigger, that would be -3, -2, -1, 0. If I go smaller, that'd be -5, -6, -7. And now I'm going to plug in these x values to find my y, so I have some more points on my graph. Now, I already know one of the y values for an x that I've selected. I have 0 in here for x. That's going to be the y-intercept. Remember, the y-intercept happens when x is 0, and I know that the y-intercept is 21. So I can throw that in my table. So now I'm going to start plugging in these x values. Just as a little insurance policy for yourself, I strongly recommend you plug your x values into the function that is already given on your paper. If you did make a mistake getting your standard form function, then when you plug in those x values, your y values are going to be plugged into an incorrect function, and so they're not going to be correct for your graph. Okay, so if you plug values into the function that you've gotten and the function that you got, the one that you wrote, is incorrect, all your y values are also going to be incorrect. It means your graph is going to be incorrect. So just as a little policy, I suggest you plug them into the function that is typed on your paper to make that work a little, maybe not necessarily easier for yourself, but to make sure you've got that sort of extra layer of security for your work. Okay, so I'm going to go ahead and plug my x values into vertex form for my function. I'm going to start here. I'm going to plug in -7 for x, so -7 plus 4 squared plus 5. -7 plus 4, remember, follow order order of operations that we reviewed yesterday, -7 plus 4 would be, -3. -3 squared would be 9. 9 plus 5 would be 14. So if I plug in -7 for x, I get 14 for y. Now I'm going to plug in -6. So -6 plus 4 squared plus 5. -6 plus 4 would be -2. -2 squared is 4. 4 plus 5 gives us 9. And then if I plug in -5, -5 plus 4 squared plus 5. -5 plus 4 is -1. -1 squared is 1. 1 plus 5 is 6. I'm going to pause there for just a second, and I'm going to plot the points that we have. So 1, 2, 3, 4, 5, 6, 7, and I believe this is 9, 10, 11, 12, 13, 14. That's up there somewhere. -6, -9, -5, 1, 2, 3, 4, 5, 6, -4, -5, or -4, 5, sorry. And then the other one we know is 0, 21, so that's like way up here somewhere. Now, I want you to remember the general shape of a parabola. We have that U shape. We know where the vertex of our parabola is, and the vertex cuts our parabola in half. We talked about this the other day. So whatever I see on this side, if I were to fold this in half along that line in the middle that goes through the vertex, this side would perfectly match up with this side because parabolas are symmetric. So that means as I'm looking at graphing a parabola or finding more y values, I can use this symmetry to my advantage. So I actually don't have to plug in the rest of these x values, right? Here's my vertex. So I know if I have a point 1 up and out on the left-hand side, I'll have a point 1 up and out on the right-hand side. I'll also have a symmetrical point for this next one up here. And if I go out one more, I should have another point that matches this guy up here. Because parabolas are symmetric, I know whatever points I see on the left, I should see on the right, and vice versa. So if I take that back to my table, here's my vertex. The y value I see here is going to be the same y value right on the other side of the vertex. And if I move out another point, I would have the same y value because those points have to be at the same height because my parabola is symmetric. And again, here, if I move out another point, if this y value is 14, then this one also has to be 14. Since parabolas are symmetric, that means my y values on either side of my vertex need to be the same. They have to be at the same height. Okay. Now, if you're not really comfortable with that idea, remember, you can still plug in -3, right? I can do that here. If I plug in -3, -3 plus 4 squared plus 5, I can still plug in that x value. So this would be 1 squared, which is 1. 1 plus 5 is 6. See? So I'll still get that value if I plug these in. This is just another way that I can approach this and sort of take advantage of the nature of parabolas. Because they're symmetric, I know that those y values have to match. I know those points have to be at the same height. Questions for me on page 12? Okay, let's try another one. On page 13, we're going to look at the same 4 representations, but this time we're starting with standard form. Remember, standard form gives me the y-intercept. So the y-intercept of my graph would be 10. That c value, that constant term at the end, is my y-intercept. And now I'm going to change from standard form into vertex form. This is something else that we practiced yesterday. Remember, we did that completing the square process. So I'm going to start by splitting up that middle term, x squared minus 3x plus something plus 10 minus something. So remember, the idea here is that this first part, I want to be able to write as x plus something squared or x minus something squared. I know that that minus 6x would have come from negative 3x and negative 3x being combined. Now I want to know, for my thing that I squared, when I did that number times itself, what was here? This would have to be 9, because negative 3 times negative 3 would give me 9. And this had to come from x minus 3 squared. Now, if I just add 9, again, we talked about this last time, if I just add 9, I change the problem, which is why we also subtract 9 off at the end. And then when I combine these last two constant terms, negative 10, or 10 minus 9, right? I get positive 1. That gives me my y coordinate for my vertex. So there's my vertex form. From here, I can identify the vertex of my function. It's going to be 3, 1. And now I'm going to fill in my table. So again, I'm going to put the vertex towards the center of my table. So 3, 1 in the middle. And then I'm going to select x values on either side of the vertex. So moving up, I would have 4, 5, 6, 7. Moving back, I would have 2, 1, and 0. When x is 0, I'm at the y-intercept, and I know my y-intercept for this graph is 10. I got that from standard form. So now I'm going to pick some values. Well, I've already picked values for x, and I'm going to plug these into my function. This time I had standard form to begin with, so I'm going to plug into standard form. So if I plug in 1, that would be 1 squared minus 6 times 1 plus 10. Remember, follow your order of operations. 1 squared is 1. 6 times 1 is 6. So 1 minus 6 plus 10. So that would be 5. When I plug in 1 for x, I get 5 for y. And now I'm going to plug in 2. So 2 squared minus 6 times 2 plus 10. 2 squared is 4 minus 6 times 2 is 12 plus 10. 4 minus 12 plus 10 would be 2. So when I plug in 2, I get 2 out. And now I'm at the vertex, which means I can use that symmetric property again. So right on the other side, right before the vertex, my y value is 2. So right after the vertex, my y value would also be 2. If I move at another point, another unit, my y value here is 5. So my y value forward would also be 5. And then I get the same thing for 10. Now I have one last value that I'll have to plug in for x. So 7 squared minus 6 times 7 plus 10. 7 squared is 49 minus 6 times 7 is 42 plus 10. 49 minus 42 plus 10 would be 17. There's my final y value for my table. Now I'm going to go ahead and graph this. So 0, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 5, 1, 2, 3, 4, 5, 2, 2, 3, 1, 4, 2, 5, 5, 6, 10, and 7, 17 is going to be way up here somewhere, so I'm not going to worry about that. Once I've plotted my points, I'm going to sketch in my parabola and throw my ends on the side, my arrows on the ends. So there are my 4 representations for this quadratic function. Questions for me on page 13. Okay, we're going to take a look at one more problem together for today. On page 14, this time we're starting with a table. Since I got the table, I'm going to go ahead and plot those points to sketch my graph. For the other problems that we did today, I got the table and then I graphed. So I'm going to do the same thing here. I have the table, so I'm going to go ahead and graph this. So 1, 2, 3, 1, -2, 1, 2, 3, 4, -1, -5, 0, -4, 1, -1, 2, 1, 2, 3, 4, 3, comma, say there's 10, 11. Now, the math teacher, like nerd in me, really wants my points to be symmetric on this graph. So even though they didn't give me these points, I'm going to go ahead and fill in those symmetric points on the left-hand side. I really like when my graphs look symmetric with their points. You don't have to do that. I'm going to, because I like when I can see that symmetry through every point that I have here. There's my graph. And now I want to get my functions, right? I want vertex form and standard form. So to be able to write those functions, I'm going to need to pick out some key information. So we could pick that key information out of a graph, and we did that the other day writing vertex form. We had a graph, we identified the vertex, and we wrote vertex form. And we can certainly see our vertex here, and we can see our y-intercept here as well. But I want to talk about how we can identify those things from the table, because sometimes that can be tricky. So we talked yesterday, I believe it was, about how to find the y-intercept from a table. We know the y-intercept happens when x is 0. So right here is our y-intercept. Okay, there's my y-intercept. I'm just going to jot that down in my standard form box. My y-intercept is -4. Now I also want to be able to pick the vertex out of the table. So that same property where parabolas are symmetric that we could use to fill out our table without having to plug in all those values, those repeating y values, right? We're going to use that same idea, this time in reverse, to be able to identify the vertex. So what I'm going to look for in my table are repeating y values. So I can see I have a y value of -1 here, and then another -1 in my y column down here. That means these are on either side of my vertex. So I'm going to follow them to the middle. Okay, so if I go in a point on each end, I have the same y value again. And if I go in on each end, I've now found the center of my repeating y values. That's the vertex. Okay, so I followed those repeating y values in to the middle. That's your vertex. So my vertex here is -1, -5. And I can see that on my graph as well. -1, -5 is our vertex there. I can also verify my y-intercept 0, -4. And now that I have these pieces of information, I can take a look at writing my functions. Now I'm going to write vertex form because the most important piece that I need to write vertex form is the vertex, which I have. The other thing I need to take a look at is that lead coefficient, that A value that we talked about. So I need to look at the way my parabola is shaped to decide if I need anything in front of my thing in parentheses that I'm squaring. So I can see this parabola opens up. If it opened down, I would need to start off with a negative. Since it opened up, I know that lead coefficient will be positive. And then I want to see if I've stretched or compressed my graph at all. So I'm going to look at how I get from the vertex to the next nice point. To get from the vertex to the next nice point, we go up 1 and out 1. That's what I expect. That matches the parent graph. So that means that my lead coefficient, that A value, would just be 1. Okay, so I don't have to worry about putting anything special in front there. If I went up 2 and out 1, I would have stretched the graph and I would need a 2 in front. If I had only gone up a half and out 1, that means I would have compressed the graph and I would need a half in front. But since I've gone up 1 and out 1, I don't need to change that A value to anything that would stretch or compress my graph. So as I go to write vertex form, again, really just a 1 here. And then in parentheses, x plus 1, remember opposite sign, squared, minus 5. So there's my vertex form function. And then I know the y-intercept is -4, and I know the y-intercept can be seen from standard form, but just knowing the y-intercept isn't enough to be able to write standard form. I need to know what that b value is for that middle term. And I can't tell that just from the y-intercept. So we're going to have to distribute vertex form to get our standard form. So x plus 1 times x plus 1 minus 5. When I distribute, I've got x squared plus 1x plus 1x plus 1 minus 5. And then I'm going to combine like terms. So for standard form, I get y equals x squared plus 2x minus 4. And if I look at my function, that constant term matches what I had for my y-intercept. So that's good. Questions for me on page 14. Okay, so for the rest of class / your homework, you have an assignment on Delta Math that's going to ask you to continue to practice determining key features of a graph based on your function form. So you're going to get questions that say something like, you want to know where the y-intercept of a graph is. Which format for your function would you like to have? I know that standard form gives me the y-intercept, so I would pick standard form. If I want to know the y-intercept, standard form would be helpful. So it'll give you the equation, and then you determine the y-intercept. Or it'll say, what's the minimum of this function? Well, we know for a parabola, if it's opening up, then our vertex is the minimum. So vertex form would be helpful for me to identify that point. Okay. Once you tell it what format you want, it'll give you that function format, and you'll be able to identify that key feature. So that's what I want you to work on for the rest of class for today, is that Delta Math assignment.